Hello my dear students, today we will study about the fourth colligative property, that is osmotic pressure. Okay, so before going into osmotic pressure, we will see what first osmosis is. Here is a diagrammatic representation of osmosis. Here we have taken two containers. In one it is a solution and second it is a solvent. This is a pure solvent and this is a solution. Solution means here solvent plus solute is there. Now the pressure acting on it is same in both cases, that is atmospheric pressure. And these two solutions are separated by means of a semi-permeable membrane. What is it? Semi-permeable membrane. Now what is the semi-permeable membrane? It is a kind of membrane which allows only a certain type of molecules to pass through it. Certain type of molecules or ions to pass through it. So in this thing, here the semi-permeable membrane only passes the solvent molecules into its solution side. The solvent molecules through the semi-permeable membrane, it will go into the solution side. Okay. Now talking about the semi-permeable membrane, actually this can be natural semi-permeable membrane. You can have natural semi-permeable membrane as well as synthetic semi-permeable membrane. Natural semi-permeable membrane means, for example, cell membrane. You all know cell membrane. Then egg membrane, and pig bladder. Pig bladder is also used as a semi-permeable membrane. These are the examples of natural semi-permeable membrane. Then talking about synthetic semi-permeable membrane, example is cellophane. Then one more example is parchment paper. Parchment paper. So cellophane and parchment paper are examples of synthetic semi-permeable membrane. And the synthetic semi-permeable membrane are continuous sheets or films that contain small submicroscopic pores in it. That is how you prepare the synthetic semi-permeable membrane. They are long sheets or films which have got network of submicroscopic pores in it. Okay. Now what is the function of this semi-permeable membrane? The function is it allows only certain kind of molecules to pass through them. So in this case it allows the solvent molecules to pass through a solution. So that is called as osmosis. So you can define osmosis as the passage of solvent molecules through a semi-permeable membrane is called osmosis. That is a simple definition of osmosis. So the passage of solvent molecules through a semi-permeable membrane is called as osmosis. Now if you say about the concentration of this solution and solvent, you can define the osmosis in two different ways. One is in terms of the concentration of solvent, and second one is in terms of the concentration of the solution. Here what I meant solution is exactly the concentration of solute. You know, solution means solute is present in the solution. Now listen carefully how I will define osmosis in terms of the concentration of the solvent. Osmosis can be defined as the passage of the solvent from its higher concentration. It means the solvent concentration is higher to its lower concentration. Here the concentration of the solvent is lower when compared to this. That is how we define the osmosis in terms of the concentration of the solvent. So you can define it as the passage of solvent molecules from its higher concentration to its lower concentration through a semi-permeable membrane. Got it? Now, how will you define osmosis in terms of the concentration of the solution? Keep in mind that when we talk about solution, we are taking solute. So, we can define osmosis as the passage of solvent molecules from a lower concentration of the solution, which means indirectly I am telling the lower concentration of the solute to a higher concentration of a solution. So, in these two ways we can define osmosis through a semi-permeable membrane. Okay, so that is about osmosis. Understood? Now we will see what is osmotic pressure. Now, osmotic pressure means, you know, the solvent molecules are flowing from solvent to solution, or a higher concentration of a solvent to a lower concentration of a solvent through a semi-permeable membrane. Now, what happens? There is an increase in the volume of the solution, correct? And you know, this flow happens till an equilibrium is attained. Am I right? An equilibrium is attained. The flow happens till an equilibrium is attained. Now, so here the volume is increasing. Now, what happens is, if I apply some pressure to the solution side in order to stop the osmosis. What do you mean by stop the osmosis? Stop the flow of the solvent molecules to the solution side. Now, you know the solvent is getting into the solution side, correct? Now, what I will do, if we apply a small pressure, the excess pressure or the extra pressure in the solution side in order to prevent the flow of the solvent molecules to the solution side, or in one word you can say to prevent osmosis, that extra pressure, if I note it as pi, P atmosphere plus pi, this pi is the extra pressure which we apply in the solution side in order to stop the osmosis. That pressure is called as what? Osmotic pressure. So, that is called as osmotic pressure. So, how will you define osmotic pressure? The excess or the extra pressure applied in the solution side in order to stop the osmosis is called as osmotic pressure. Now, what will be the pressure in the solution side here? P atmosphere plus pi. Now, pi is the extra pressure. Now, we got it. What is osmotic pressure? Okay. Now, you know that osmotic pressure is a colligative property we discussed earlier. Now, being a colligative property, it depends only on what? The number of solute particles. So, the pi depends only on the number of solute particles. Now, we are considering only dilute solutions, correct? All the colligative property we discussed, only we are considering dilute solutions. So, in dilute solutions, experimentally it is proven that pi is the osmotic pressure, is directly proportional to the concentration. Pi is directly proportional to concentration. Now, what is the concentration here we are taking? We are taking volume, right? We are considering the volume here. So, what will be the concentration related to volume? It is nothing but the molarity. Here is the difference between this colligative property and the three other colligative property which we discussed earlier. In all other three colligative property, you know we discussed about the molality, that is about the solvent. But here we are considering molarity, that is we are taking the volume of solution in liter. That is the difference between this method and the other three methods. Now, coming back, this osmotic pressure is directly proportional to the concentration. Concentration we relate to the molarity, correct? Again, this osmotic pressure is directly proportional to temperature. Then we can have these two equations as pi is proportional to C into T, correct? Now, in order to remove the proportionality, you will have pi is equal to C into R into T. So, this is our basic equation. Pi being the osmotic pressure, C is the concentration which is molarity, R actually it is called as the solution constant. You know, we term it as universal gas constant because both are having the same value, and the T is temperature in Kelvin. So, this is the fundamental equation for finding out the osmotic pressure. Correct? Now, from this equation, how will you derive the equation for finding out the molar mass? You know, we are finding out the molar mass of the solute, or you represent it by B, right? Now, how will you calculate the molar mass of the solute? Now, going back to this concentration, molarity is nothing but M is equal to number of moles of solute by volume of solution in liter, right? So, I can write this C as number of moles N of solute means NB by volume of solution in liter. Am I right? So, I can write here pi is equal to C. For C, I can write NB by V, correct, into RT. Okay. Now, what will become? Pi V is equal to NB into RT, correct. Now, is there any relation this pi V is equal to nRT with any other equation? You know, what is it? For an ideal gas equation, PV is equal to nRT. The same equation related for the gas. In solution, pi V is equal to NB by RT. Now, coming back to what is NB, number of moles is equal to mass of what? The solute by molar mass of the solute. Correct? Now, putting this equation here, pi V is equal to molar mass, you can write it as WB. Okay, WB into RT by capital MB, or MB is equal to WB RT by pi into V. So, see, by this equation we can calculate the molar mass of the solute. So, you understood? First equation with pi proportional to molarity, then temperature, then both, then proportionality sign with the R, then change the concentration into the molarity, that is NB by V. So, putting that, you will get pi V is equal to NBRT. Now, putting the value of NB as WB by MP, you will get MB is equal to WBRT by pi V. So, this is the derivation for finding out the molar mass of the solute. Understood? Okay. Now, we will see some of the advantages of osmotic pressure method compared to the other three colligative properties. What are the advantages of using this osmotic pressure method? The first advantage is, as you know, we use molarity instead of molality, correct? Second is the pressure measurements. You have measured the pressure, that is the osmotic pressure means the excess pressure. That pressure measurements are done, the pressure measurements are done in room temperature, isn't it? Standard temperature. The pressure measurements are done in room temperature. That is the second advantage of using this osmotic pressure method. Now, the third point is the magnitude is high. What is magnitude? That is the value. The magnitude is high even in dilute solutions. That is the third advantage. The magnitude means the value we get is high in dilute solutions. The fourth advantage is by using this osmotic pressure method, we can calculate the molar mass of macromolecules. We can calculate the molar mass of the macromolecules. Now, what is macromolecules? Example, like polymers. You will study in last chapters in organic polymers, or you can say biomolecules. These are the examples of macromolecules. So, by this method, it is easy to calculate the molar mass of the macromolecules. So, these are the 4 advantages of using the osmotic pressure method when compared to the other methods. One is molarity is using instead of molality. Pressure measurements are done at room temperature. The magnitude or the value is high even in dilute solutions, and you can calculate the molar mass of macromolecules. For example, polymers and biomolecules. You know, these polymers are unstable at high temperature. The polymers are unstable at higher temperature. That is why this method is useful for polymers. Okay, these biomolecules also are unstable at higher temperatures, and polymers are also having poor solubility. Just for your information, you just note it as you can find the molar mass of macromolecules, that's all. So, these are the advantages of using this osmotic pressure. This is very, very important. Board exam, they can ask you, give 2 advantages of osmotic pressure when compared to the other colligative property. Clear? Okay. Now, moving on to a small topic which is called as isotonic solution. Isotonic solution. Now, what do you mean by isotonic solution? Example, if we have 2 solutions having same osmotic pressure, I have 2 solutions having same osmotic pressure, that is pi and pi. Then these solutions are called as what? Isotonic solutions. So, if 2 solutions having the same when 2 solutions are having same osmotic pressure, pi and pi, it is called as an isotonic solution. Clear? So, when 2 solutions having the same osmotic pressure pi, for example, pi 1, if we have a solution having an osmotic pressure pi 1, another solution having an osmotic pressure pi 2, if pi 1 is equal to pi 2, then we call the solution to be isotonic solution. Okay. Now, one interesting fact about this isotonic solution is, you know, the osmotic pressure of our blood cell. In biology you will study, right? The osmotic pressure of our blood cell is equal to the osmotic pressure of 0.9% NaCl solution or saline water. Just recall it. The osmotic pressure of our blood cell is equal to the osmotic pressure of 0.9%, means it must be mass by volume. You know that to represent the concentration. 0.9% of NaCl solution, which means what? You can inject or you can give the saline water into the body without any disturbance or without any difficulty. Why? Because the concentration of both these are what? Same, or the osmotic pressure both are same. That is why it is safe to inject this saline water intravenously. Correct? So, this is regarding our blood cell. So, these are the isotonic solutions, example of isotonic solution. Now, if I draw a representation regarding this, see, listen carefully, this is our cell, blood cell, correct? And this is the saline water. Okay. When a blood cell is put in a saline water and the concentration of saline water is what? 0.9% of mass by volume solution, correct? Now, what will happen? Is any osmosis takes place here? No. Why? Why? Because the osmotic pressure of this blood cell is equal to the osmotic pressure of the NaCl solution. Okay. Now, let us see what will happen if we put a blood cell into a solution of NaCl having a concentration greater than 0.9%. I repeat, what will happen when a blood cell is put in an NaCl solution or brine solution having a concentration of what? 0.9% mass by weight. What will happen? Here the concentration is high, correct? Now, what osmosis does? Osmosis means the passage of the solvent molecules from a lower concentration of the solution side to a higher concentration of the solution, correct? Now, here the concentration of the NaCl is high. So, what will happen? The water molecules from the cell comes out of the cell and making the shell shrink. That is happening. So, the cell will shrink. And such a solution where the concentration is greater is called as hypertonic solution. Got it? So, a solution in which the osmotic pressure is greater than the other one is called as a hypertonic solution. For example, if this is pi 1 and if you say pi 2, we can say pi 1 is greater than pi 2. So, this is an example of a hypertonic solution. Okay. Now, we will see the second case. That means, if a cell is dipped in an NaCl concentration whose concentration is less than 0.9%, what will happen? You know, here the concentration is lesser, correct? Concentration is less, and here the concentration is greater. That is a solute concentration. I am talking about the solute concentration, correct? Now, what will happen? The NaCl will, from the NaCl solution, the water will go into the cell, making the cell what? Bulgy, correct? So, these are the, and such a solution is called as what? Hypotonic solution. So, two types of solutions are there, hypertonic and hypotonic. Here what happens? Pi 1 is less than pi 2. So, these are the three cases regarding the osmotic pressure. So, here it is what? It is an isotonic solution, correct? Isotonic solution means pi 1 is equal to pi 2. Here it is a hypertonic solution, that is pi 1 is greater than pi 2, where the cell shrinks. Here the cell will bulges out, that is called as hypotonic solution, that is here pi 1 is less than pi 2. You got it? So, this is all about what? Isotonic solution, hypertonic solution and hypotonic solution. Understood? Okay. Now, we will move on to certain phenomena where we will see the osmosis happens. Now, we will talk about certain phenomena which can be explained by this osmosis. Simple, some examples which you are seeing in daily life. Okay. Then the first one is simple examples. Raw mango, you know, right? Raw mangoes, when placed in brine solution, it will shrink. Now, you know how it happens. Think about it. The raw mangoes, when placed in brine solution, it will shrink. Now, the second is wilted flowers. You know what is it, right? Wilted flowers revive. Wilted flowers revive when placed in fresh water. This here also osmosis happens. Now, third example is, you know what? Plants take water, correct? Plants take water and nutrients. Plants take water and nutrients from roots, isn't it? With the help of what? Osmosis. So many examples I can give you. Just for the sake of it, we will see the 3, 1. Okay. Now, we will have another important example, that is the medical condition called edema. Have you heard of that? Medical condition edema. That is also, you can explain this edema in terms of osmosis. What is exactly the edema? Edema is nothing but the swellness or puffness due to the water retention in tissues and intercellular spaces. You got it? Edema means it is the puffness or swellness due to the water retention in tissues and intercellular spaces, or the fluid is getting into the tissues or into the intercellular spaces, making them swelling. Okay, so that is also, this edema can be also explained in terms of osmosis. So these are the certain phenomena which can be explained by means of osmosis. Okay. Okay. Now we will see the last thing, that is, till now we have studied about what? Till now we have studied about osmosis. Now we will see what is reverse osmosis. Now what is reverse osmosis? By seeing the name itself, it is saying that the osmosis is getting reversed, isn't it? Now what is osmosis? Osmosis is the flow of solvent molecules from the solvent side into the solution side. Okay. Now I will give a diagrammatic representation how the osmosis works. Suppose this is fresh water, okay, and this is salt water. Here I am applying the pressure, okay, with the piston. Okay. Now what happens is, we can reverse the direction of osmosis. You know what is osmosis, correct? So you can reverse the direction of osmosis if a pressure larger than the osmotic pressure is applied on the solution side. That's it. This is the solvent and this is the solution, correct? Now what reverse osmosis says? If you apply a pressure greater than the osmotic pressure. What is osmotic pressure? Osmotic pressure is the excess pressure which is needed to stop the osmosis. Now if we give a pressure which is greater than the osmotic pressure, what will happen? The solvent from the solution will move into the solvent side, correct? By means of a semi-permeable membrane. You got it? So by applying a pressure which is greater than the osmotic pressure, we can have the flow of the solvent molecules from the solution side to the solvent side. The best example is desalination of seawater. Desalination of seawater. Here what happens? When the pressure is more than the osmotic pressure is applied, the pure water is squeezed out from the seawater through the membrane, making the seawater pure water for drinking, isn't it? Potable water. So that is the application of what? Reverse osmosis. Normally in the reverse osmosis, the SPM used is cellulose acetate. Normally the SPM or the semi-permeable membrane used for the reverse osmosis is cellulose acetate. This cellulose acetate is permeable to water, but it is impermeable to the impurities and ions present in seawater. That is how we get what? Pure water for drinking through reverse osmosis. Correct? So nowadays in many countries, these desalination plants are there to meet their potable water requirements. So this is about reverse osmosis. Okay. Hope you have understood osmosis, the osmotic pressure as well as the reverse osmosis. Okay. So please revise this portion, read the textbook thoroughly. Until the next section, take care and thank you.